I'm going to tell them, Wayne.
No, you can't.
We need to tell them.
No, OCR wants it quiet, they want it shh.
But they don't own us, Wayne, they don't own us.
Oh, we are right in our own, but Simon Cowell.
Oh, well, I think Simon Cowell would respect this decision.
Okay, we'll just tell them, we'll just tell them.
Okay. So this is all about Kepler's third law, but he didn't just have a third law.
No, that's a common misunderstanding.
Yeah, we had a first and second before, that's how you get to 3.
It is.
In the first place. Yeah.
And you don't have to know either of the first and second laws, it's all a conspiracy.
But I think you should.
Yeah.
Yeah. So his first law
Quite simply says
that planets orbit bodies in an elliptical motion.
it's not a circle, they're not orbiting in a circle, it's an ellipse that they follow around something.
So that's the sun, this is an orange pen, it's very exciting.
Your orbit would look something like this. An ellipse, rather than a perfect circle.
Not a very elongated ellipse, it's more elongated for Pluto or whatever, but
Yeah.
say this is us, this is more what it
So
is.
the sun isn't perfectly in the centre of
Yeah.
your orbit, is what his first law states.
A bit like fried egg.
A bit like a fried egg.
Things like that, yeah.
Second law.
Second law,
This
yeah.
is one of my favourite ones.
It's good. So you have different speeds, essentially.
When you're really far away, you're actually moving slower than when you're here.
So find out why.
Per unit time, let's just say 4 days, that's just a random time.
Yeah.
You keep it the same. Every 4 days you measure where the Earth is. It's going to move a little bit, it's going to move a little bit more, because it's going to be accelerating.
Yeah.
So down here it's going to move quite far. I mean,
Yeah.
this, I'm not drawing this out.
It probably isn't going to be 4 days. So you can't
Oh
have
yeah,
more than 4 days.
Otherwise we'd orbit in a couple of days.
Yeah.
But an amount of time,
Yeah.
it's going to move different amounts because it's moving quicker here.
Yeah. And if you draw an imaginary line from the centre of the sun to each of these dots and form loads of triangles all the way around, so there, and then I just go straight to the side.
Yeah. Here, per unit time, it's moved loads around its elliptical orbit.
But the radius isn't very long.
So it will have X area.
Yeah. But because the radius is really long here, it'll actually have the same area.
And that's the incredible thing. Every single sector has the same area because when it's moving much quicker,
Yeah.
it's got a much lower radius.
And that's really cool.
It is.
And that's part of how he got to his third law, which in loose terms is, kind of like the quote, but it is t squared, straight proportional
To r cubed.
to r cubed.
Well, this is the period of the thing orbiting, and the radius is the radius between the thing orbiting and the thing it's orbiting.
Yeah. But when you say t squared proportional, it's a constant, right? It's a constant.
Yeah. Fish hate constants.
They hate constants.
So t squared must equal.
Sorry,
Fish
sorry.
would hate
Oh,
that. No fish would hate
They
that.
would not like it, right? Very quickly.
K r cubed, and the question becomes, what is this k?
What is the constant? It's quite hefty. So I think first we should write down what we know.
So
It'll take a long time actually. Maybe just some of the gravitational
some
things.
of the physics things
Yeah.
we know.
Okay.
So we know that F is equal to G M
Yeah.
M over R squared.
We also know that F is equal to mv squared over r.
We do, because that's remembering back when we did roller coasters and stuff, the
Mm.
same thing is applied for planets. It's
Yeah.
a circle, it's a circular motion.
But that also means it's going to have a circular velocity, right?
Yep, which is what this is, but we express it in a different way.
Yeah. So remember when it's essentially speed is equal to distance over time.
Yep, but in a circle, the distance is actually the circumference.
Yeah.
So 2 pi r. And t becomes capital T for period rather than just time.
Yeah.
So if I express this in a slightly neater way,
Okay. You can sort of put v squared next to the m over v. 'Cause
m
that's-
over r times
sorry,
r
sorry.
v squared.
Yeah.
So v is now this.
So it becomes
2
2 pi r over t squared. So
Yeah,
that looks quite untidy, so we'll put it together, I think.
So we get a result of f equals m,
Mm-hmm.
4, because that's been squared,
Yeah.
pi squared r squared over rt squared.
Whew. So we have that. Now wait, I've noticed something.
Right.
That equals f.
It does equal f.
And that equals f.
It does, so we can equate those.
We can say that they equal each other. So if we do that,
So this must equal g m m over r squared.
now we can do some rearranging.
We can, because this is horrific.
Yeah, so what I'll do, I think what we do first is just times both sides by the top bit of that.
Yeah.
So if you do that,
Well,
we
divide both sides by g m over
Oh,
m.
sorry, yes, yeah.
So what we're going to get is m for pi squared r squared, because that's not going to change.
Over what we had before, which is our t squared, but as well our g and both our m's.
G, m, it's ridiculous.
And our m's then will cancel over 1 over r squared. But here, this m, say, doesn't really matter which, and this m will cancel.
Yeah. So they'll just be completely gone.
Yeah, they'll be gone. Well, we cancel the 1.
Then what I do is I times by t squared.
Okay.
Because what we're trying to get to is t squared k r cubed.
That's what you want.
So I'd want t squared on the simpler side.
And while we're there, I think I'd remove this r and make that just r.
Yeah, so this r disappears and
And
that's
then the
reduced to
squared.
just 1.
Yep. But then if you go to the next stage where I was talking about, so we now have,
T squared over r squared
yeah, straight the other way around, why not?
is equal to all of this without the t squared. So
Yeah.
4 pi squared r, because remember we just reduced the r to cancel, over gmn.
Gm.
Gm, sorry, it's dotted out. I'll do it in a different colour.
Sorry, wasn't as clear. So now we can times both sides by r squared,
Yeah, we can.
which I'll just do like this.
Just do that, yeah. T squared equals, and then that r is going to become r cubed.
It is.
Times by r squared.
So that's kind of similar to this way.
It is. That we want it in a form of t squared, which we've got.
Yeah.
So we're, in terms of graphs, which is what they've used,
Yeah.
t squared equals, oh sorry, we've got y
Yeah.
equals mx in terms of a line. We've got no plus constant. Now at the minute, our x is our r cubed,
Yeah.
and that's with all this stuff. So we write it in a slightly
So
different
yeah,
way.
so basically we separate it. I'll write it up here so you can see it clearer hopefully. So we can write t squared and equals, and we can separate this out like we did before.
Yeah.
So we'll have our 4 pi squared over gm, put that in brackets.
And times it all by r cubed.
Yeah.
Then we've got it in this form y equals mx. So this
This thing here must be,
our
A
k,
constant.
or our gradient if we're plotting graphs.
yeah, constant.
Constant.
So that's why that's a thing, and that's Kepler's third law. So when you use that, we use it when you're going around planets and you're
Yeah.
trying to find the period. Often you'll just be talking about these relationships and the distances, maybe in the double the radius, you'll talk about how it affects the period. That can be a bit confusing as 1's cubed and 1's squared.
They love the Earth with satellites.
Yeah. And the moon, which I guess is a satellite as well.
Yeah. They love the Sun with the Earth.
Yeah.
And they love Jupiter with its many, many moons, and
It
the
has
differences
got many
between
moons.
the moons as well. It actually
Yeah.
likes it. If it asks about Jupiter, what it will tend to do is ask about a moon, then say there's another moon further out, or
Yeah.
whatever. What's the
Say,
difference?
yeah, what's the difference, and then
what's the ratio between the radiuses, say?
yeah,
Which is easier than it sounds.
and you can use this as a ratio, so that's fine.
4 pi squared over gm is constant, but the m is the mass of the thing you're orbiting.
Oh, that's an important thing. Yeah, the m is the thing, the central point that you're going around.
So you don't
and that
need
will
to know
change.
the mass of this satellite.
No, you didn't know, that at all. And here you need the mass of the sun, and only the mass of the Jupiter, which is an important thing.
R cubed is obviously the radius between the centre
Yeah.
and the satellite.
So often people sort of just do it between the surface and the satellite, so the distance between the satellite and the Earth, really need to do that plus the distance to the centre of the Earth.
Yeah.
That's our centre of gravity.
Yeah. Often in the question they'll give you the radius of the Earth, and people overlook it. They forget it. They say they'll tell you this radius here,
Yeah.
and then they'll tell you this radius here, but
And-
earlier on in the question, then they'll
Yeah.
word the rest of the question.
Yeah.
So hopefully you'll forget the number, but don't do that.
Don't do that. Yeah, always write down everything you have, anything you need, and it'll hopefully become more obvious then.
That's a whopper of an equation, a whopper of
is.
a derivation.
One of those.
Yep.
Yeah.
But you might have to do that, you might have to know.
Yeah.
We'll see you at the next video.
Alright.
I like Kepler.
I think he's great.